right, chapter 11. So we're going to look at what is the definite integral today. So we do have to flash back to lesson 10.4, which you may or may not have loved. I'm guessing didn't love, but recall that the limit as n goes to infinity of the sum from I equals 1 to n of f of xi times the change in x, where the change in x is b minus a on n, and xi is defined as a plus that change in x, arises in finding the area under the curve y equals f of x from a to b. So just a reminder of our pieces. This is really the width of our rectangle. This xi equals a plus lets us know which x is being inputted to the function to give me my unique y's. And what we're doing here is summing up the areas of all the rectangles that we have put underneath our curve. And then as we increase the number of rectangles, then we get an area that fits pretty darn close to what the area under that curve is, right? That's what happens, right? The more rectangles we have, the more accurate our area is. Well, limits of this form also arise in computing lengths of curves, areas of surfaces, and physical quantities such as work and force. And since this type of limit occurs so frequently, it's given a special name, the definite integral of f from a to b. So we have our formal definition. Let f be a continuous function defined on an interval from a to b, and that definite integral of f from a to b is, this is the one that we worked with, from the integral from a to b of f of x dx is equal to the limit as n goes to infinity in terms of x. Okay, so this is the one that you were familiar with that could be done in terms of y. And we did do one question in terms of y, but we really didn't look at it from a limit perspective. We just kind of turned the graph on our side 90 degrees and we looked at it. I think that was in lesson 10 too. But it is allowed for you to do it in terms of y instead of in terms of x. So this whole thing, remember flash back to chapter 2. This limit occurs so frequently. Remember, we ended chapter 1 and started chapter 2, which is the beginning of derivatives. And it was like, oh, it's called the derivative. This limit, the H formula limit, occurs so frequently, it's called the derivative. So this limit is happening so frequently, we call it the definite integral. So just a little reminder, the integral sign was first introduced by Leibniz. In the notation that's given here, f of x is called the integrand. I don't think we've talked about that. A is the lower limit, b is the upper limit. We've talked about that. And dx, just remember dx simply means that the integration process is in terms of x. It's not a multiplier, okay? It's just, remember when we do the substitution rule and we change it to du, it means that we're integrating in terms of the variable u. So it's really important that we still have that piece in our notation as we are writing out our work, okay? So an indefinite integral has no upper and lower limits, and it's written without those a's and b's. Okay, and it results in a function. In fact, it's a family of functions because we have the plus c on those ones. We're working with definite integrals, so they're going to have those upper and lower limits, and therefore we're going to result in a number. Okay, that's what we're looking for today. And this whole procedure of calculating the integral is called integration. So what's basically chapter 11 is about. More integration. Okay, example 1. Evaluate the integral from 0 to 5 of the function 3x minus x squared in terms of x using the definition. Okay, that means use the limit formula with sigma notation. Okay, so when it said calculate the derivative using the definition or using first principles, that was our limit formula. So here it is again. So we are going to need to start out with finding all of our information. Okay, so A is my lower limit, 0. B, my upper, 5. The change in x will be b minus a on n. So 5 minus 0 on n, 5 on n. Okay, and then I need to know f of xi. So let's look at xi's little formula is a plus I change in x. So a for us is 0 plus I times the change in x we calculated as 5 on n. And so we need f of 5i on n. And that would go into my function, which was 3x. Whoopsies, forgot my 3. Okay, 3 times, let's write out f of x. 3x minus x squared. So 3 times fi on n minus, that's a squared, really, I promise. Fi on n squared, which when you calculate that, you get 15i on n minus 25i squared on n squared. Okay, so now that we have our two pieces for our limit formula, we're going to fill out the limit formula. Okay, so the limit as n goes to infinity from I equals 1 to n. So we have f of xi, which is 15i on n minus 25i squared on n squared, being multiplied to the change in x, which is 5 on n. Okay, so I'm using my limit formula. The limit as n goes to infinity of the sum of f of xi times the change in x. Okay, and then we can go ahead and work through this so that we can expand and get to a spot where we can use those little sigma notation expressions for our i's and our I squareds from our chapter 10 lesson, 10.4 lesson. So if you have your chapter 10 notes handy, you might want to refer to that first page of the 10.4 notes to find your formulas. Okay, so we have the limit, and you have to keep writing your limit and your sigma notation. You can't drop those until we've gotten to a spot where we can do some replacement. So I'm going to multiply this in. Sorry, I keep scrolling up and down. I'm going to multiply this in first before I start to move things around. So 15 times 5 is 75i on n squared minus 25 times 5 is 125 I squared on n cubed. Put that in a set of brackets, and now I'll scroll. Okay, at this point, we're really back to our chapter 10, 10.4 lesson, working with those sigmas. So I want to give each of these their own sigma and factor out the constant piece. I'm going to take out the 75 on n squared and then leave the I minus, let's give these each their own sigma. So 125 on n cubed and leave the sigma for I squared. And now these have formulas, okay? That was the point. We want to replace those with the formulas from that 10.4 lesson, okay? So we're still having a limit, so we still need to write that out. But we can now replace the sum of I from I equals 1 to n. This formula is n times n plus 1 on 2 minus 125 on n cubed. And this one, I squares formula is n times n plus 1 times 2n plus 1 on 6. And I'm going to put one more set of crazy brackets in there because it's the limit of the whole thing. Okay, so from here, the limit as n goes to infinity of, I'm going to just see what I can cancel a little bit. I can kick this and this out. I have a 75 on 2. I'm going to actually put that in the front. So let's give myself a little more room here of the limit. And then I'm left with n plus 1 on n minus 125 on 6 limit as n goes to infinity. So now I'm using my properties of limits. What could we tidy up here? So I have an n. I'm going to make that an n squared. Okay, and expand this one out. You get 2n squared plus 3n plus 1 on n squared. And now you can calculate your limits as n goes to infinity, just like we did way back in chapter 1. Okay, so 75 on 2, the limit as n goes to infinity. Remember, these ones you divide by the highest exponent. In the case of the first limit, it's just n minus 125 on 6, the limit as n goes to infinity, 2n squared. So this one's highest exponent is n squared. And you have to write really small to get it to all fit. Okay, so as n gets infinitely large, look for the ones that are going to go to 0. This one's going to go to 0 and leave me with, this is equal to 75 on 2. This whole limit, the first limit is n on n divided by n on n. So that's just 1. Minus 125 on 6. What's happening over here? So 3n on n squared is going to 0. 1 on n squared is going to tend to 0. And then I'm left with calculating this piece, which is just 2. And when you simplify this, you get the answer to be negative 25 on 6. Now, it's okay for this to be negative because this is asking us what is the integral, not the area. Okay, so really what we now know is that the integral from 0 to 5 of 3x minus x squared in terms of x is equal to negative 25 on 6. We're evaluating the integral in terms of the definition formula, not area, okay? That's really important to notice the difference. You can always check your answer using your antiderivative, okay? So if I took the antiderivative of 3x, I would get 3/2 x squared, and the antiderivative of x squared is 1/3 x cubed, and evaluate that from 0 to 5. And when you do that, you put in your 5, really, because the 0 is just 0. And so you're doing 3/2 times 5 squared minus 1/3 times 5 cubed. Subtract 0. And it actually works out to be exactly the same. Okay? So it's okay for these integrals to come out to be negative because we're really just evaluating the integral using this definition, this limit formula. Okay? It's different when it asks us to calculate area. All right, pause the video here, and I'll see you back for example 2.